Hello everyone, my name is Vikram Madan and I'm a Principal Product Manager on the AWS Machine Learning team. And today I'm very excited to be co-presenting with Dr. Sam Huddleston, who's a technology lead at the NFL's Digital Athlete Program. Today we're going to be covering how the NFL creates their computer vision training data sets at scale. I'm going to kick things off by giving you a quick overview on AWS's human-in-the-loop services. I'm going to then hand it off to Sam, who's going to talk about specifically his helmet impact detection use case. He's then going to cover best practices around how to label video data specifically at scale. And then he's going to close things out with a demo and a very, very cool call to action. Now, where I want to start off is just quickly giving an overview of each stage of the machine learning lifecycle, and then also explaining how the human-in-the-loop services plug into each phase. Now, this is an iterative cycle, and basically where everything begins is with the data and preparing the data. This could include any type of pre-processing. It also includes human labeling of the data. Once you have a data set, then you move into the build stage. And this is where you choose an algorithm or you build an algorithm that is specifically required by your use case. Once you have an algorithm and you have your data, you're now ready to train a model. And basically, you can fine-tune this model to achieve the accuracy level that you require for your use case. Now, once you have a trained model, you're ready to deploy this into production and integrate it with your specific application business logic. Now, SageMaker is meant to help you throughout this end-to-end process. And specifically, SageMaker provides a couple of human-in-the-loop service components that you can use, first of all, in the prepare phase, where you're labeling data at scale, which is Amazon SageMaker Ground Truth, and where you can use to review predictions produced by your trained model. This is Amazon Augmented AI. That essentially serves as a human backstop to those predictions. Say if your confidence is below a certain threshold, and that confidence is outputted by your model, right? So if it's below a certain threshold, you can review it before you send it upstream to higher levels of your business logic. So today we're going to deep dive into Amazon SageMaker Ground Truth, which is a service that the NFL used for their specific use case. And where I want to begin the discussion is talking about why we released SageMaker Ground Truth. Now, you use SageMaker Ground Truth for supervised learning use cases. And these are basically techniques that you can use to train a system to learn from ground truth data. In other words, data that is labeled by a human, right? Now, many of the advances that you've heard about in deep learning or with neural networks are supervised learning techniques. And when you're employing these techniques, they require a lot of data. And that data needs to be very highly accurately labeled. And what we saw with these types of projects that leverage supervised learning techniques is that they led to massive project bloat. At nearly 80% of those projects, the time and resources invested were spent on the upfront data labeling. Hence, we launched SageMaker Ground Truth 2 years ago at reInvent 2018. SageMaker Ground Truth is a fully managed service that allows you to easily and accurately label your training data. Ground Truth also provides you many of the best practices and security features that you've become accustomed to with other AWS services. Now, in terms of making data labeling easy, right, Ground Truth provides over 30 data labeling workflows that you can just pull off the shelf. These are built-in labeling workflows. And with each of these built-in labeling workflows, we provide a number of algorithmic capabilities. One of them is assistive tooling. So these are tools that are backed by algorithms, and these tools are baked into the UI that the human labelers use to do their work. In addition, we provide an auto-labeling capability. And this auto-labeling capability basically learns from what the human labelers are doing and is able to auto-label a portion of your data set. And this saves time from your labelers having to do that work instead. And then finally, there's accuracy improvement algorithms. One of the primary ones is a consensus-based algorithm that takes input from multiple workers and consolidates it into high-fidelity labels. In addition, with ground truth, you can use your choice of human workforce to actually perform the labeling. And then finally, a pretty unique aspect of this service is it's pay-as-you-go. We also offer volume-based discounts for committed volumes, and those are through private pricing arrangements. Now next, I want to talk about the 30-plus data labeling workflows. When we launched in 2018, we started off with workflows for 2D images as well as text. In 2019, we launched a number of audit workflows. These are workflows that are meant to review the accuracy of your data labels, as well as update those labels to ensure that they're meeting your accuracy thresholds. We also have a very robust custom workflow framework where you can design and build your own custom labeling workflows for your specific use case and basically plug that into ground truth and run labeling jobs using that custom workflow. Now this year in 2020, we're very excited to launch 2 new major capabilities that help really deepen our computer vision coverage. And these are for 2 very complex data types. It is video and 3D point cloud. Now with these complex data types, it requires a lot of human effort to label them. And that's why we've heavily invested in assistive tooling that makes the lives of the human labelers much easier. Now, Sam's going to cover the video workflows in depth because of his use case, but the similar type of approaches also applied to the 3D point cloud space as well. Now, moving on to close things out, I just want to quickly cover the human workforce options that we provide. The first is Mechanical Turk, and this is a globally distributed, crowdsourced workforce that can work on your labeling tasks on demand. So they can pick up your tasks and work on them 24/7, 365 days a year. In addition, you can use the private workforce option. And this is where you onboard your own workers. And this is particularly useful when you are dealing with sensitive data, or you have labeling. You have a labeling use case that requires specialized skills. Then thirdly, we have a vibrant marketplace of third-party vendors. And these vendors meet a particularly high security bar. They are SOC 2 certified, as well as they must pass an AWS application security audit. And then they're listed on our marketplace, and you can use them directly through SageMaker Ground Truth. Now, one of the unique aspects of Ground Truth that I want to call out is you can use a mix and match of these options, right? And this is exactly what Sam and his team did at the NFL, where they started off with a vendor, and that vendor did the first pass of labeling. But then they augmented that by bringing on a subject matter expert who would review the output from the vendors and ensure it met the quality and accuracy threshold that they required before using it in training their model. So with that, I want to close and hand it off to Sam, who will take us through his use case. Off to you, Sam.
Thank you, Vikram. I'm Sam Huddleston. I'm the tech lead for the NFL's Digital Athlete Program. I support player health and safety initiatives in the NFL with research and technology that makes the game safer. Today I'm going to talk to you about a specific use case, a research data set that we are working to develop. Right now, every year, we conduct a video review of 48 games a year in order to tag the helmet impacts that are experienced by players during the game. This is a research data set that we use to support a bunch of different initiatives around making the game safer. One of those research initiatives allows us to go to players and help coach improve technique through an initiative we call Heads Up Football. By analyzing the scenarios and the positions that players put themselves in, we can illustrate to them ways that they could better protect themselves as they block or as they tackle. And that case cascades down through multiple levels of football. We also have implemented some rule changes in the NFL based on this research data set. And some examples of rule changes from this include some changes to the kickoff rules to remove scenarios where helmet impacts occur. We've also removed the blindside block from the game, based at least partially on research from this initiative. And as you can see in the image to the right, which illustrates two players who are lowering their heads to initiate contact, we've implemented a rule to remove this scenario from the game. Because players who lower their helmets to make contact have a much higher risk of injury in that scenario. And so now, after this last year, there's a rule that makes that a foul. And we've seen a great reduction in that behavior on field. Finally, we are also using this research data set to help us design better helmets. So you can imagine that an offensive lineman might experience a very different kind of helmet impact than, say, a cornerback or a wide receiver who are moving at a really high speed in the open field. So this research data set allows us to see the kinds of scenarios that players are in when they experience a helmet impact, where those impacts take place, and then we can design helmets that are better for a specific position, improving safety overall. These various research initiatives and rule changes, coaching improvements, and better helmet design have had a profound effect on the number of concussions in the NFL. Over this multi-year program, we've been able to reduce concussions about 30% year over year during the course of this program. Now, the specific thing that we tag as we go through this is a definitive helmet impact, also known as an exposure. A definitive helmet impact occurs when we can see that the trajectory of the helmet changes upon contact. And we have a whole bunch of video reviewers that help us with this task each year. What I'm going to do is I'm going to give you the opportunity to take a look at what that might look like. So what I want you to do is to watch this video and identify all the definitive helmet impacts or exposures that you see occur while the play unfolds. Now, there was a lot of activity happening in that play. I'm sure that you identified all 22 definitive helmet impacts that occurred in that play. Or maybe not, because this is actually a pretty tough labeling task. We have about 165 plays a game. We have 22 players on the field. And we have multiple views. And so what we have to do in order to generate this research data set is do what we just did about 7,000 times a game or more. Because for every play, we have the video reviewers watch every player individually and document those helmet impacts. It's very difficult for us to scale this research up, more than we have right now. And so we are actively working on developing a computer vision technology to automatically identify helmet impacts as they occur in video. And later on, I'm going to talk about an opportunity that you have to contribute to that work as well. So in order to develop this computer vision technology, we need a lot of labeled data. And so what I'm going to do is talk you through the labeling procedures that we used, leveraging the ground truth system in order to develop a research data set specifically for training computer vision and machine learning algorithms to solve this problem. As I mentioned, we have some historical data because we do this research program every year where we label these videos. And so our starting point was a historical data set from 2018 and 2019 that documents at the player and play level the exposures that are experienced by players, right? So I have this player and this play had maybe 2 helmet impacts. But what I don't have is I don't have that marked on the video per se. And so what we have done is that we've taken video of these plays and fed it into the ground truth labeling system, working internally and then with vendors in order to label every helmet in every frame of every play. It's a very intensive data set to put together. Then we have a video review expert who reviews both the labeling that comes back from our vendor partners and also takes the known helmet impacts that we have documented in our historical data sets and matches those up, producing a very high fidelity research data set that we can use. Now, what we then do is that we take those data sets and we submit them to our machine learning teams. And they use them to build machine learning models to solve this problem. And obviously what happens is they identify maybe there's some shortcomings or there's some things that you could do that would improve our work. And so then we start the process over with those key lessons learned being implemented. So what we've done so far in this research program, designed to build a computer vision system for identifying helmet impacts, is that first we built a data set that we labeled ourselves, kind of small scale to get a feel for the problem. Then we launched it out to a vendor with the ground truth system. And we provided those results to our machine learning team. And they came back and through an iterative process, we discovered some really important lessons learned, which we then implemented and went back to the vendor and generated the data set that you'll get an opportunity to see later if you'd like. And so what I want to do is talk you through some of the key lessons learned we discovered by going through this highly iterative process, labeling things ourselves, then evaluating the responses coming back from vendors, and then finally going at scale and generating a very large data set. The first lesson learned has to do with syncing the multiple perspectives that we have of the video. If you take a look here, I have a snapshot at the beginning of a play, both from the sideline view in the left panel and from the end zone view of the play in the right panel. And what I want you to notice is that in both of these images, number 21, who's in the lower left corner of the right panel, has his hand raised. And you can see that these are synced. When we first started using these videos, we're feeding multiple perspectives of the play into the labeling system. And what we had not done is time synced those. But what we discovered as part of our machine learning work is that having a synced view of the play really helped our machine learning algorithms and also really helped with the labeling. Because if you see something happen on frame 110 in one video, then you could expect to go looking for that in the other perspective. And so what we did is that we implemented a pre-processing step that would allow us to sync these videos before they went out the door, so that when we get labels back, those labels are synced with each other. Then we cut the videos so that they start at the exact same time. The next key lesson learned had to do with improving our labeling scheme. Our first round that we sent out to the vendor, we didn't specify the particular label that each helmet or player was supposed to have. And so as the labelers saw a helmet in the first frame, they would label the first one helmet 1, the second one helmet 2. But we discovered that there was a problem that was popping up for our machine learning teams. And the issue, this issue happens a great deal in data sets that involve tracking, especially tracking with collision. And what was happening was that when two players collide, there was a tendency for the labels that were on those helmets to switch. And so we would not have the same player labeled all the way throughout the play. We also had players that would leave the frame where the video pans away and then come back in, and when they re-entered the picture, they would have a new label attached to their helmet. So what we did was we leveraged a key data store that we have called the Next Gen Stats system that tracks players and their location throughout the game. And what we did is we generated a reference diagram for our labelers. And so the first frame that they see in any play as they begin to label shows them, the home team is in white and the visiting team is in black, and there's a specific label, which is the jersey number of the player that is put on this reference diagram. That allows the labelers, even if they can't see a player's jersey number at the start of the video, to correctly label each player. Then, as the play unfolds, due to the assistive tracking support from the AI system, those helmets are tracked with the assistive tooling. And so if we get the first frame right, the assistive tooling pretty much solves the labeling problem and assists the labeler in keeping the correct label on the player. And if there is a collision or something like that happens, it's quite obvious when a label has been switched, because most collisions occur between players on opposite team. And the label provides a clear indicator starting with V for visitor or H for home team that indicates which team they're on and how that should work, right? So it becomes quite simple for us to keep track of whether or not the right thing has happened. And the combination of the assistive tooling and the new labeling scheme completely eliminated the label switching between players in our data sets. Another key lesson learned was in using tags to add context. So I mentioned in the last slide that we have a unique label for every player. However, there's two scenarios where it becomes uncertain what label it is to put on a player. One of those scenarios is often there are big pileups. If there's a fumble, there will be a lot of players in the same space piled up on one another, and you might see a helmet, but you don't know who the player is. All you see is a helmet that's in a pile or sticking out of the pile. And we need a label put on that, but we don't know the player. And so we generated some catch-all labels, V00, meaning an unknown player on the visiting team, and 800, meaning an unknown player on the home team. Then what we were able to do is allow them to use that whenever they see that scenario. But then another scenario popped up, which you can see in the image on this slide. And that is that we have players on the sideline who are often wearing a helmet who will appear in the video, and we have to account for that. And so this feature was actually added at my request. I can generate a conditional requirement. You can see a little bit of code there from the SageMaker CLI, such that if somebody wants to use a label that has 00, they have to provide an indicator of whether that player is on the field or on the sideline. And that allows our machine learning models to make a distinction as we fit them. And we can remove things from consideration that we don't want to use in our models. And it's been really helpful. Finally, the last big lesson learned just concerns how we manage all of this at scale. We have databases now, we have our compute, and our labeling workflows are now all housed within Amazon Web Services. And so when we're generating a job, I just talked about many of the pre-processing steps that we need to do, right? We need to get a list of players who need to be labeled for a play. And we programmatically create a list of labels that is specific to that particular play and that particular view. And then we launch this reference diagram and put it at the beginning of the video. We also, as I discussed, have to sync the videos before we ship them. And so that requires some pre-processing step, and we've just built a pipeline that uses the snap time in order to help align that. Then we're launching the jobs, right? We're sending the job out to the ground truth system, and we're using SageMaker to launch those jobs at scale, to monitor their performance or completion as those jobs are being executed. And then as those jobs are completed, they come back and we audit those jobs. So I've thrown a graphic in here of one of the audit checks that we do in the top right corner. What we do is we take a look at the label size that's happening in the images from frame to frame. And the labels shouldn't change very much, right, as they come in, because it's one video tracking it. So we expect some consistency there. And if we see some significant jumps in the size of the labels that are being generated, that's an indicator that there might be some quality issues. And we can use SageMaker to simply relaunch those jobs in an audit status to make sure that somebody takes a good look and cleans it up. Once we're happy and we've passed audit checks, these data sets get turned over to our machine learning teams. And they're actually trying to develop the helmet impact algorithms. They're developing algorithms for tracking helmets, for detecting helmets on field, et cetera. And then we're evaluating the performance of those models. So I've also included a picture of one of the visualizations we use to evaluate a model that's coming out. And this evaluation is based on detecting the helmets that are actually in each frame from left to right. And you can see the snap is a vertical line there. And what we're looking for is lots of green. Green means a perfect assessment of what happened. Red indicates a misdetection, and blue indicates a detection that shouldn't have been there, a false positive. And so as we review these, what we're doing is we're evaluating the scenarios where our machine learning models are having trouble solving the problem. And what that allows us to do is identify specific gaps, maybe in the labeling data that we have, scenarios that we need more examples of. And so then we take that gap, that identified gap in our labeling support, and we start the process all over again. As we go through each one of these turns, we're scaling up. And what really makes this work for us is being able to prepare, build, train, and tune. And while we are not yet at the deploy phase of this technology, we're iterating through these stages. And so we're using SageMaker and the SageMaker CLI to do this at scale, because not having an integrated environment would make this much more difficult. What I want to do now is show you the outcome of this process. So this is a first play. Same play that we saw before, viewed from the sideline. And what I want you to notice is the extremely good tracking capability that's demonstrated there. These helmets are tracked through every single frame, and the bounding boxes are tight. And a lot of that has to do with a combination of the assistance provided by the AI combined with a human conducting a quality check as it advances. Here's the other view. You've seen this before. This time we're going to include the labels as this play unfolds. And what you might notice is some red flashes that are happening while this play unfolds. And those red flashes are, as you can see here, the moment of impact, which we have now labeled. Now, what I'm really excited about here is that you have the opportunity to take a good look at these labels and all of this workflow, because we have a Kaggle competition that's active right now that you're welcome to participate in. This Kaggle competition basically is to try to develop a computer vision technology to automatically detect helmet impacts on field. There's $75,000 in prizes. You might have the opportunity to get interviewed on NFL Network about how you solved the problem, and you get the chance to help improve the safety of the game of football, both at the NFL and quite possibly all the way down through all the different levels of football, college and high school and Pee Wee, because you're helping us to develop research data sets that support a better understanding of how we can protect athletes. We really hope you participate. I'm really appreciative of you spending time in our talk. So thank you for attending, and we'd love it if you could complete the survey and let us know what you thought. Thanks.